back, everyone. To kick off our morning of talks, we have Julien from Sequent, who will be talking about Python data visualization. Let's make him feel welcome.
Hi, everyone. So yes, I'm Julien from Sequent. Hopefully, that nice little picture on the left will make sense as I go around the slides. Also, I'm the second French speaker today, so I feel a bit bad about it. Sorry about it. So without further ado, a quick presentation of Sequent. You've seen the nice videos. Fun fact is Sequent was created 20 years ago by mathematicians from the University of Canterbury and from a medical application for handheld scanner, basically moving to geological modeling. 20 years on, Sequent is a massive leader in geoscience space here. Now, quick word about me. I have a degree in physics and engineering, then switched to working in software engineering, mostly in finance, first in Paris, London. And then 4 years ago, I relocated to Christchurch, where I worked I've been working in the Leapfrog engineering team as a software engineer, and now software engineering manager. I play guitar. Handball as well. You can see me throw angrily a ball at people. It's not a workplace picture, so don't be scared. And I also have a family, and we enjoy skiing, hiking. Now, I'm going to give you a quick overview of Leapfrog so that you understand the context in which I'm talking today. Briefly introduce the tools that I'm pretty sure you're all very familiar with, and then provide 4 use cases of using these tools within the software engineering department. Before we dig into the topic, so this is a screenshot of Leapfrog. You can see Leapfrog as a powerful calculation engine coupled with a 3D visualization engine based on OpenGL. The code has been started 25 years ago. We have millions of lines of code over several code repositories. We've got 40 people in the engineering team alone for Leapfrog, 5 dedicated product owners. We're releasing the software twice a year. And in every release, we more or less have up to 30 to 50 new features, which range from small improvements to existing ones to very large new initiatives. So if you look at the software, it's pretty simple. I would say on the left-hand side, you have the base of geological modeling, your drilling data that you can import. And from that drilling data, you can create a geological model, numeric models, etc. And once those models have been calculated, you can basically visualize them on the scene. So 3D. I didn't want to give a live demo. I know how tricky this is, so you'll have to just do with a picture. And the bottom part is basically all the colorings that you can tweak. So in here you have some drilling. You can see the drilling going down in the scene, and the outline of a surface that's built from a numeric model. If you want to know more, there's plenty of material online. About the tools that we are using, I think you're all familiar with NumPy, scientific computing, pandas to aggregate data, easily import, export to CSV, Excel, and you name it. Plotly, basically taking data from NumPy and pandas and turning it into nice visual diagrams. And last but not least, Graphviz was not technically pure Python. But there's a nice Python library on top, and which is turning object dependency, a description of object dependency, into nice dependency diagrams. Now, to my very first case, I'm just going to go briefly about that. As I mentioned, we have a very large engineering team, a lot of people working, large features to develop. We are trying to turn the work we're doing into something that can several teams or several people can easily collaborate on. So we are turning basically Jira tickets, which are quite a flat description with dependencies, blocks and blocked by, into a nice diagram, just leveraging a small web service running with Flask, interacting with the Jira REST API, feeding that data to Graphviz, and just getting a kind of nice outline. Obviously, this is a kind of simplistic diagram of dependencies, and this is how we're going to organize the work. This is a bit more complicated example of a breakdown of work that we're doing, and it's still pretty simple. So just to let you know that, yeah, we're using those tools quite often, and we have very large dependency diagrams that helps us, plan and perform the work. Now, my next use case is around performance. As I mentioned, Leapfrog is a big calculation engine. We can describe it as a large tree of dependencies of objects that are using other objects as inputs, basically. So this is a simple description. Let's imagine that your object A is drilling data, and of that drilling data, you've built two numerical models, B and C. Obviously, as soon as you update your drilling data, there's some processing done on that drilling data, cleaning up, rebuilding some dependencies, and then basically the two numeric models will be pushed in the queue to be processed. In that example, we have two processes dedicated to the calculation engine, in which case, basic parallelization of the two numeric models once the drilling data has been done. Now, what is the problem we're trying to solve? Our customers have massive geological models. We're talking about thousands of objects, large drilling database, massive amount of imported data, and when they come back to us complaining that their models are very slow to process, what do we do? Luckily, our application collects processing data in real time, and this is a source of information for us. So what can we do? Obviously, we try to identify the slowest task that we call blocks. We try to find the dependency bottlenecks. Also, there's some long processing chains, because all the objects are dependent on each other. So we have collected flat data about blocks, so every task, the time every task takes to complete, along with information about the dependency chain. So from a very flat, CSV type data, we can easily use pandas to just aggregate that data, sorted by total processing time on the bottom part. So this is very simplistic, but if you look at the data just quickly, first finding, we have one long-running, unique single object. So obviously, this needs to be looked at. Second findings, we have a very large amount of objects that have a very small average running time, but cumulated, that represents a lot of data. And last but not least, we have, in average, some blocks or tasks that take quite large. So that gives us an idea of what we should be focusing our efforts on. This is just one way of looking at the data, as I said, simplistic. Second way is, how do we make sure that the parallelization is efficient? And how do we identify when processes are basically idle? That's where Plotly comes into the picture. So in that graph, our calculation engine has 8 processes available to parallelize the calculations. And we turn the flat data that I showed you before into a data that's grouped by processes and then sorted by time. And using Plotly timeline charts, you can get that nice, pretty good-looking diagram. So the colors correspond to a certain block type. So as you can see, for instance, the red blocks are quite big to process, but they're pretty well parallelized. Now, instantly, if you look at that graph, you can see that there's a lot of idle time in the processing. And that's easily highlighted. If you look at the green block, it's probably a dependency of the other blocks, which that diagram doesn't show, but you can infer it. So it means the processing of that block should be clearly improved. It's the same. Earlier in the graph, you can see that there are 2 smaller bottlenecks. And our goal is basically to compress all that processing to limit the time, the total time we're spending to process a project. Finally, some of you are probably familiar with code profiling tools. Obviously, they work well for when you're profiling a code that's executed sequentially. Now, in a distributed model like the one we have, getting that kind of high-level view is harder. So using Graphviz this time, feeding on the same data, we managed to get something that probably looks very familiar to the Python profiler, code profiler tools that we have. But instead of line of code or functions here, we have complete blocks, which are objects to the process. So on the left-hand side, it's a view that's being filtered by biggest contributor. On the right-hand side, a complete graph more complete but still filtered, because obviously there are a lot of objects. But that provides a very good overview to identify long processing chains, basically. Now, the following two use cases are R&D use case. So, as I mentioned earlier, the core of the business for Sequent is about surface modeling. So getting surface modeling tools that are efficient. One of the algorithms that can be used to generate surface is marching cubes. So the way it works is basically you have a grid of points, and if you've listened to the talk before, you have voxel data, which is massive amount of 3D data in space. So that's what you have on the left-hand side within a bounding box. There's a slight difference in coloring that corresponds to the numerical values associated to all the points in space. The middle picture is basically that data filtered using the threshold that we want to use to build a surface. And finally, the last one is the actual surface. So as you can see, the raw data, the filtered value that you can easily get inside Leapfrog, because we have tools to filter data, obviously easily in the scene. But then generating a surface, a triangulated mesh from that surface, can be done using marching cubes. So now, a word about marching cubes. And I'm going to start explaining the concept using marching squares. So that technique has been developed in the 80s to basically generate surface from scanner data. Simply, some of you might already be familiar, so I'll just go quickly over it. If you take your data, which is in that case a big square, and you have plenty of smaller squares, and each squares are basically looked at independently, and you're basically checking if the vertices of each square are within or without the surface. And on the left-hand side, obviously, the first example is you have no points inside. Second one, the red dot, your surface is inside, so you have to basically, the surface is somehow cutting that corner. And the remaining two examples is the surface is cutting in half, and so marching square, 4Ks, pretty straightforward to model and engineer. And how does that work? Basically, once you've kind of looked at each square independently, you map them together. And the fact that the squares are sharing an edge enforces that the surface has a smooth profile. It's like all connecting together. Hope that makes sense. Now, if we're looking at 3D, obviously, it gets a bit more complicated. I'm not going to go into details, but you basically have 14 different configurations that you can get for your triangulations. And that makes it really interesting from an engineering standpoint. Why is that interesting? So first of all, what is marching cubes trying to do? Imagine that your cube is made up of 8 vertices, numerical values, and we're basically trying to provide an approximation of what a curve built by interpolating the values in any point in the cube would look like. And that's what you have on the left-hand side. So we've defined a threshold, and we've used a trilinear approximation to find exactly where that threshold value was going through. And using Plotly and Scatter3D plot, you can basically build the outline of that surface. It's basically what you're trying to approximate when you're doing marching cubes. On the right-hand side, the same, approximated by triangulations, obviously this time using Mesh 3D from Plotly. It's surprisingly quite easy to get those 3D diagrams going. It gets a little bit getting used to, but then you can get some pretty interesting results. We are a software engineering company. There are plenty of research implementation of marching cubes. None of them are kind of easy to use, I would say. And when the research papers were published or the code was published, some other people pointed out of issues in the code, and that's resulting from the combinatory logic of marching cubes. So you imagine you have 8 vertices that can be either inside or outside. That gives you 256 possible configurations. First one, all your points are inside or outside, which is called case 0. Case number 1, only one vertex of your cube one vertex of your cube is within the cube, so you have 8 configurations, but you also have the reverse configuration where you only have 1 point outside. And then case number 2, same logic with an edge, 1 out of 12 edges, 24 configurations. So that's just giving you a little overview of the complexity. You have 256 possible configurations, each relating to one case. In addition to this complexity, some cases have what they call ambiguity, and this is case number 13, which was just one item in one of my first slides. It actually translates into 6 different possible configurations, and each of those configurations can lead to different combinatory logic based on how they are built. So that makes the whole problem very complicated to solve in a safe way, let's say. Last but not least, we are a company that's specializing in surface modeling. So creating the surface is one thing, but we're using that surface as a volume. And a big aspect is to be able to check if points are within or inside or outside a volume. And to be able to check that, basically you need to make sure that your surface is also correctly oriented. So you need to make sure that the normals to your triangles that you're creating are pointing the right way, which makes, once again, the problem a bit more complicated. So why go into the hassle of building our own libraries and looking and building all those 3D visualization tools? Well, the point is, there's no easy way to check the things you're generating. Marching cubes is leveraging lookup tables. So basically, you get your configuration, your 8 vertices, that will turn into an integer based on the values of then point to a concrete case. There is ambiguity resolution afterwards, which makes it even more complicated. And you finally get to a triangulation that's more or less hard-coded in a lookup table. Generating lookup tables that are not flawed from inception is really hard. And having the ability to visually inspect the result is massively important. So in that case, I took a very concrete scenario with numerical values. As you can see, the purple outline is the trilinear curve, which basically doesn't lie. This is what the surface should look like within the cube. And on the other side, I have the triangulation I tried applying based on my lookup table, and obviously, I got it completely wrong. And this is massively important to get that right. Now, we got a prototype working in Python. And Python is amazing to build prototypes because you get results very, very fast. What can we run that prototype, we generate a surface, that surface looks good. What information can we get out of it? So as I said, we have plenty of cubes that are handled independently in our big bounding box. The first result that we can get using pandas is collect metrics around the triangulation. And one aspect is that among all the cubes that we tried out to try and triangulate, basically less than 5% of those cubes were actually triangulated. Most of them were fully inside or fully outside the volume we are trying to look at. First, important bit of information. Second one, for all the triangulations that we've applied, basically collecting which case they correspond to and build a nice diagram. So it's probably not obvious for someone who's not into it, but the cases that are highlighted here, 1, 2, 5, 8, 9, in that diagram are basically cases that are non-ambiguous, meaning you have a straight resolution from your configuration to a triangulation. Those two information combined, as I said, we have a Python implementation. Obviously, we want that to be extremely fast, so we're considering pushing it down to C++ or Rust or technology that's really fast. That information basically tells us that we should be good at discriminating the cubes that are not inside our surface, but also we should be focusing on handling the standard scenarios because these are the most regular ones, basically. Second R&D, and that's trickling from that work on marching cubes, is how do we evaluate if the volume that we're creating or surface we're creating is of good quality? So as you can imagine, 3D visualization in an engine like Leapfrog is heavily based on triangulated meshes. The meshes can be internally generated from numeric models. They can come from CAD softwares, like Bentley has CAD software. They can also be imported from third-party packages, etc. So you get a different range of meshes that have different quality. They are quite often used to cut, like for instance, if you imagine a tunnel design, you import the tunnel design from CAD software, and then you run it through your geological model to understand which geological layers you're going through. So those operations of cutting, etc., are very common. Problem is, if your input meshes are of bad quality and you're using them to cut and merge, etc., with other meshes, you're basically compounding bad surface quality. So it's quite important in that context to check if the surface that we're generating internally, at least, have a quality that's up to standard. So how do you evaluate if surface is good? So first of all, you want to avoid skinny triangles that are very long triangles that are going through your surface. That happens quite often. So how do you spot them? Well, one way is just to use a simple ratio of your in circle and circumcircle of your triangle. That will give you a number between 0 and 0.5, the maximum being for equilateral triangle, obviously, and the generated triangle would be 0. And for simplicity, multiplying that number by 2 so that your value is within the range 0, 1. Another way of looking at the triangle quality is basically take your mesh, look at the biggest triangle in terms of area, and basically divide all the other triangle areas by that one same. You will get a value between 0 and 1, and that makes it easy for you to spot which triangles are actually small inside your mesh. Small triangles can be a problem as well. So this is theory. What do I do now? So collecting that information, all our meshes are represented using numpy arrays of coordinates, basically. So it's pretty straightforward to calculate either the triangle quality or the triangle size using simple pandas functions. So I'm not going to show you any code. That would be a waste of your time. What is the end result? So if we calculate for our mesh our triangle quality and triangle size, and at the bottom part you have the distribution of the triangle quality using a histogram of Plotly, and at the bottom part the triangle size distribution. As you can see, we have quite a lot of triangles that have like a very poor quality on the low end, and also quite a large amount of very, very small triangles, particularly like triangles are extremely, extremely small. So how do we tackle the problem of improving the triangle quality? So I'm not going to go into details because I'm running out of time, but you can basically adapt your triangulations when you're running marching cubes to use to remove what they call edge groups, which are basically an edge group is the way you triangulate. You create a triangle between the edges of a cube. And you can basically swap 4 triangles with 6 triangles leveraging the centroid of your cube. And there are lots of research papers about edge groups and how some specific edge groups, configuration if you want, of edges will lead to poor surface quality. So, okay, all fine, we have that document. How do we make sure that actually the surface? So using same metrics, you can generate candlestick diagrams. So these are all the triangles and which edge group has been used to generate them. And as you can see, indeed, the edge group number 2 has, in average, a pretty low quality. I don't know if, I guess you're familiar with candlestick diagrams, but basically the center is the mean, so it gives you an idea of, and then you have the quartiles on the side. So edge group number 2 is pretty bad, and so adopting a new triangulation, and edge group number 2 and 3 in that picture are going to disappear. And the red line is just giving you the minimum kind of level. With a new triangulation, getting rid of those 2 edge groups, so edge group 2 and 3 are gone here. As you can see, overall, our triangle quality has improved quite a lot. So, what's the impact on the surface for triangle quality? On the top end, the darker triangles are the ones who have a poor triangle quality. After applying our technique of using different triangulation, as you can see, there are far less triangles with bad quality, and the baseline is much lower. So this is pretty good. Now, how do I improve triangle size? Well, simply, as you can see, I have a very, very small triangle in the middle, leading to very skinny triangles like a star-shaped effect. Very basic thing you can do in that case is just cluster the points. Just merge the points together, you get rid of the central triangles, and you also get rid of the star-shaped ones that are stemming from them. So same, if we apply that technique to a mesh, if you look at the top, you can see those very weird thinny triangles at the top. At the bottom, they are all gone. And there's a very sharp cut around the triangle size here, which is exactly what we were trying to achieve, get rid of all the, the peak that was at the start. So my final slide is just comparing the results. So as you can see, this is the initial mesh without any optimizations. This is the one applying the 2 optimizations. We've basically nearly got rid of all the bad triangle with a very bad quality. And basically any triangle quality above 0.15 is kind of deemed acceptable. And also the triangle size distribution, we've cut off all the very skinny small triangles that we had at the start. So I'm just going to stop here for today and open it for questions. I'm sorry about the absence of Python code, but I think it was more interesting to explain what we're doing and how we're using the tools. Oh, yeah. So this is a picture of my desk, or what should I say when I turn around. Sometimes, yeah, we're a dog-friendly workplace, so yeah, we have very, very big dogs. Yep. Any questions?
We have 2 minutes for questions. Who has questions about different types of triangles? No? No? Bueller?
I was just a quick one, wondering about how you normally use Plotly. Are you just running that in notebooks, or do you have your own tool that you've built?
Some of them are integrated as kind of what we call development tools in the platform. So, when you're generating a surface, as a developer, we can use additional. So we just include it. Or we can run scripts. I mean, sometimes we export to CSV or Excel, and then we use independent scripts to kind of parse the data and then produce it. For instance, for processing times, we have a bunch of existing projects that we're kind of looking for as benchmarks, and all that exporting is done automatically to CSV, and then we have a separate process kind of handling all the parsing and generating the data for us. But it's on a case-by-case basis.
One more question. Going. Let's thank Julien again. We have more talks, but there's 10 minutes while we change out our speakers, so sit tight.